Hello everyone, today I'm very happy to introduce my research paper at Social NLP. The title of our paper is Stance Inference in Twitter Through Graph Convolutional Collaborative Filtering Networks with Minimal Supervision. This paper is in collaboration with Eric Lehalt. Let me now introduce you to the problem and the motivation. The motivation behind our research is to address the limitations of existing methods for predicting user stances on social media platforms, especially Twitter. Researchers still face several challenges in this task, including dealing with informal language and the brevity of social media text. These models are limited in determining user attitudes. We aim to improve content-based collaborative filtering approaches and develop a more accurate and efficient model for stance prediction. This will enable us better understanding of social and political movements. Our contributions can be summarized in three aspects. First, we propose a semi-supervised model that requires minimum annotation, making it more efficient and practical for real-world applications. Second, with our model, users' stances can be represented in a continuous space, providing a better understanding of their positions on different topics. Third, we conducted extensive experiments on two large Twitter datasets to validate the effectiveness and robustness of our approach. Before diving into the details of our work, I would like to provide some background on the previous research that inspired our study. In the field of stance detection, researchers have developed several approaches. The hashtag-based studies have relied on hashtags in tweets to improve stance classification. Semi-supervised methods, on the other hand, aim to minimize the need for label data by exploiting the structures of the data. Considering user homophily, the inclusion of additional features could strengthen stance inference. These features include user following relationships and mentioning retweeting behaviors. In addition, latent relationships may be valuable by establishing connections between users who lack direct connections. To effectively exploit these features, collaborative filtering is a good choice. It includes matrix factorization-based and graph-based methods. Both approaches can extract valuable information such as community structures from the input data. To assess the robustness of our method, we conducted experiments on real Twitter datasets, focusing on the Chilean constitutional referendums in 2020 and 2022. For data collection, we first looked at the followers of the Chilean news outlets, as these individuals are more likely to have formed opinions. Before each referendum, we chose a specific window of time and collected tweets and profiles of these millions of users within that period. To remove noise and unnecessary information, we applied three filters. First, we removed users who followed more than 10 news outlets. Second, we kept users whose location included both Santiago and Chile. And third, we excluded hyperactive accounts that posted more than 3 tweets per day on average, as these accounts could belong to organizations or companies, while our purpose is to infer the attitudes of regular users. For later analysis, we also normalized and manually annotated the embedded hashtags. The table below shows the details of our datasets. After the collections and filters, each dataset has over 30,000 users and millions of tweets containing thousands of hashtags. After annotating the top 500 hashtags of each dataset, we identified 40 and 55 hashtags related to the referendums in 3 classes, namely positive, negative, and neutral. After data collection, we followed a standard routine to process the tweets containing hashtags. We assumed that these hashtags could represent different attitudes in some way. So we used existing embedding techniques to encode the hashtags. From the plot, we observed that hashtags with different attitudes are well separated. This observation confirmed our assumption that hashtags can represent user stances. To infer users' most relevant hashtags, we propose a model that is a variation of LightGCM, but including weighted links of the graph. The model is called WLGCM. The inputs to the model include a user hashtag interaction graph with weighted links, as well as latent and visible user-to-user relationship graphs. These inputs propagate through three convolutional layers, generating embeddings for both users and hashtags. After aggregation and inner product operations, we can determine the affinity between hashtags and users. A higher affinity indicates a stronger preference. We used a triplet loss function that is optimized using a Bayesian personalized ranking method. In our experiments, we compared the WLGCM model to several baselines, including a null model with randomly generated interactions, a matrix factorization method with negative sampling, and the state-of-the-art LightGCM. We evaluated the performance of these models at both age and user levels. At the age level, we reported recall and NDCG scores for the top K recommendations. At the user level, we reserved 5% of the users and their interactions with referendum-related hashtags as ground truths prior to training. After training, we obtained the affinities of these users for the same hashtags. For both the ground truths and the affinities, we divided users into different stances and calculate the classification accuracy. This table shows the performance of the models at both age and user levels. Compared to the non-model, other methods are able to capture non-trivial features. The graph-based methods generally outperforms the matrix factorization in most cases, with the WLGCM models achieving the best result at both levels. For the model variants, we observed that different features contribute differently to the performance. The integration of pre-trained hashtag embeddings usually allows the model to make better predictions. Social features also help improve the performance over the baselines, but their combination proves still to be challenging, at least at the age level. In addition to the aforementioned experiments, we also examine the impact of hashtag annotations on the accuracy of the model. For the first dataset, accuracy increased at a slower rate than the number of annotated hashtags. For the second dataset, accuracy initially increased but plateaued even as more relevant hashtags were annotated. Thus, it appears that it is not necessary to identify all relevant hashtags, and having more doesn't significantly improve accuracy. This observation could potentially save us from time-consuming manual annotation tasks. So far, I have introduced our work on the WLGCM model. In summary, our model shows improvement of 3.4% in recall and 3.6% in accuracy compared to the state-of-the-art. In addition, the model requires minimal annotations for each stance, and these annotations are used only for user classification. However, we also recognize several challenges that need to be addressed. First, we aim to find an effective approach for incorporating multiple relationships. Second, the Chilean referendum datasets reveal an interesting shift in public opinion, which initially favored the 2020 referendum but reversed within 2 years. Further research could track this shift and identify the events or reasons behind it. Finally, while this study only annotated hashtags with 3 labels, it could be also beneficial to explore stance characterization in more complex discussions. Thank you for your attention. If you have any questions, feel free to ask.